Welcome from my side to this meetup and to the next half an hour about the publication Martin Schmidt, who's sitting here in the second row, myself, Simon Steineber, Konrad Schreiber, and Benjamin Roth, published on the NLP last year. As this guy implies attention, I'd like to start with Donald Trump. A group of researchers analyzed Twitter users during the presidential election in the United States in 2016. They used sentiment analysis to define 6 specific groups of users. The whatever user who's not politically engaged at all, the Trump supporter as well as the Hillary supporter, and the positive, neutral, and negative user, which is writing about one or both candidates in a negative, positive, or neutral way. One of the really interesting results was that the politically engaged user, like the Hillary or the Trump supporter, tends to build communities and is strongly connected to users from the same class. A second result was that the positive user is not building communities. And if you look at it from the other way around, you could say a user with a wider perspective tends to write more positive. But as this talk is not about social media or its influences on politics, I'd like to come to the question, what is sentiment analysis? It basically is a text classification problem with the goal to assign a sentiment to a given text. The difficulty can range from assigning, classifying a text as negative or positive to more fine-grained sentiments like positive, neutral, negative, or positive, semi-positive. It might be more clear if you look at an example. This is a tweet about the Deutsche Bahn, and the user here is on one hand happy that the strike is over. Can you see the laser pointer in the back, or is it? Okay, sorry. And on the other hand, he's complaining about the Deutsche Bahn, that they are rising their ticket prices. So in overall, we could label this sentence or tweet as neutral. If you now wonder that I have mentioned aspects in the beginning why I did this, I will come to that now. Yeah, if you look at the example again, and we don't analyze the whole text, but we look at topics mentioned in the text, we could see at one hand that the user is talking about the ticket purchase and he's complaining about it. So we would label this aspect as negative. On the other hand, he's also happy that the strike is over, so in a general way, he's speaking positive. This problem or task is called aspect-based sentiment analysis. And it's basically a combination of a multi-class labeling and a normal class labeling classification problem, as you have both the aspect extraction or labeling and a sentiment analysis part to it. After this short introduction, I hope you're excited about to hear how this all works on a technical side. Our system is structured into these 4 components, and I will approach each component by the 4 questions. Where does the data come from? How does the machine understand words? How does the machine understand the meaning of words? And how does the machine express itself? So where's the data coming from? We use the German competition from 2017 as our base. It's providing 22,000 annotated messages from the context of the Deutsche Bahn in German language. It also provides a baseline system consisting of a support vector machine using term frequency and German sentiment lexicon. As the competition has been completed, we could use the best submissions to the competition as the state of the art for our publication. And it also provides an evaluation script which is using a micro average of 1 score, so we could ensure that our comparison to other systems is computed correctly. Here you can see a small snippet from the data set, which has been provided in XML format. You see the example from before, here's in German language. You can see the overall sentiment, which is here defined as neutral. And you see here in the options section the definition of the mentioned aspects, allgemein, which is general, and Ticketkauf, which is ticket purchase, and their sentiment. As you can see here, it's possible that the data, that the text can be labeled with more than one aspect. The data has been split into a train set, which we use to train our models, a development set, which we use to compare our methods or systems with each other, and a test set, which we use to compare to other systems as the submissions of the competition. To give you a feeling for the difficulty we have to deal with, I'd like to tell you some statistics about the data. On the left-hand side, you could see the distribution of the overall sentiment in the training data set, and as you can see, most of the data numbers, 68% of the texts, are labeled as neutral. Therefore, we have to deal with the difficulties of imbalanced data. On the right-hand side, you can see a snippet from the distribution of the aspects. Overall, the data set defines 20 aspects, with the most frequent, the general aspect, with around 12,000 occurrences, and the package aspect with only 12 occurrences. So you can see that the aspects are even more imbalanced than the sentiments.
So how many aspects in total?
It's 20 aspects in total. Yeah. So after you have a feeling for the data, I'd like to talk about how does the machine understand words. Very effective and also well-known approach is word2vec, which has been introduced in 2013. The idea here is to learn the meaning of a specific word, here declared as the focus word, by looking at the context the word is used in. So here in this example, we learn the meaning of the word learning by looking at the 4 words before and the 4 words after the actual word. Therefore, we train a simple neural net with one hidden layer, using one hot encodings of our context words to predict our focus word as the output. After the training phase, we could exploit our weight matrix from the slide before, which is used here, and take the rows as our word embeddings. As our texts are German language, which is a morphologically rich language, as you can see here, for example conjugation, you have a lot of different word forms. To deal with this problem, we used fast text, which is sharing the idea of learning the meaning by looking at the context. But you don't take whole words, but you learn the meaning of subwords. As you can see here, if you compute the representation of gehe, which means I go, you add the representation of GEH and the representation of EHE. For the representation of gehst, which means you go, you also take the representation of GEH as just M of the word, and add these 2 representations. So you can see we can deal with the similarity between those words, but we also have the slightly difference between those words encoded in our representation. A third approach of understanding words is you don't encode your words, but you encode characters. The advantage of this approach is that you make your system resistant against unknown words as you only take characters. Here you can see an example from OpenAI, which trained a model to predict the next character in Amazon reviews. And after training, they analyzed the network and they found a neuron which was matching the sentiment of the text at the specific time. You can see this here. The green color means that it's really a positive sentiment, and here in the red part is a really, really negative sentiment. The downside of this approach is that you need a lot of data. As it has been stated by Chang in 2015, it only works when you have millions of texts. And for example, the research group of OpenAI used 82 million Amazon reviews. But if you want to use the advantages of character embeddings, you could use a neural network or a part of a neural network to compress one-hot encodings of characters and compress them to a representation of your word, which is then processed. We also tried the combination of different embedding methods. As you can see here, this is a small comparison on the development training set. You can see that fast text is working better than word2vec in this case, and improves massively if you add a character embedding to the fast text embedding. As our machine now can understand words, I'd like to come to the next part, the encoder, or the question, how does the machine understand the meaning of words? Therefore, we compared two kinds of neural networks. One is the convolutional neural network, and another one is the recurrent. Who thinks of image classification first when he hears convolutional neural network? I'd like to briefly explain how you use this technique on words instead of images. As you can see here, we have the word embeddings of our given text as the input, and the filters of the convolutional layer work on the whole embedding and then on the desired number of words, which will be referred to as the filter sizes. As our results showed that the convolutional approach is outperforming the recurrent approach, I won't go into detail about the recurrent, but if anybody has a question about it, I've prepared a slide for the question and answer section. So, after this really short section about how our machine can understand the meaning of words, I'd like to come to the next question, how a machine expresses itself. We dense the output of our encoder by using a fully connected layer, and then we dense it even more on a hidden layer with the size that is representing our number of classes. Like in our case, the 3 classes, negative, neutral, and positive. And we use softmax to compute the probability, and then just select the class with the highest probability as our result. Now you might wonder, how does our system take aspects into account? Therefore, we have again 2 different approaches. The first one is the pipeline approach, and the second one is the end-to-end approach. The pipeline approach consists of 2 steps. The first one is using an aspect classifier to extract, or as in our case, the aspects are predefined, classify the text by which aspects are mentioned in it. Afterwards, we use this result and our initial data and the sentiment classifier to compute the output. In this case, we have to use the text on each aspect we identified here on its own. We again have two options how we could inject the aspect into our system. The first one is on the embedding level. So we take a representation of our aspect and just concatenate it to each word embedding of our sentence. Then the concatenated embeddings are processed as usual. Second approach or second option is using attention. As the attention algorithm is kind of complex to explain and has been outperformed by the embedding concatenation. I won't go into detail here, but if anybody has a question, you know how this game works. And another interesting thing I might mention here is that we used mod aspects to compare these two techniques, so the results are not influenced by the accuracy of our aspect classifier. The second approach is simplifying our system by not using a second classifier, but compute and output in an end-to-end approach. So we only have our data, a sentiment classifier, and our desired output. Therefore, we have to adjust the output. And as you can see here, we compute for each aspect if it's mentioned in the text and if it is mentioned with what sentiment is it mentioned. To come to the end, I like to compare our system with the best submission, the baseline, and the techniques I explained. You can see that both approaches, the recurrent and the convolutional approach, are performing better when they're using the end-to-end structure instead of the pipeline structure. You also can see that our system is outperforming the baseline and the best submission to the competition by around 6 to 7%. This is the this is the F1 score I mentioned in the beginning. Yeah. That's been it. If anybody wants to know any details, I have a link to the paper here, and I also open sourced the code we used on Bitbucket. I don't know if you have access to the slides.
Yeah, we can share them.
Yeah, we will share them. Yep, that's been it.
Do you need another info? I think we just get the questions from the audience.
Yep.
Do we need a moderator? Brauchen wir die Moderation?
Schon. I don't know. Yep.
Yeah, I have a question.
Haben wir ein Mikro?
Ja, Mikro. Wo?
Nee, wir haben...
Perfect. Hello, test. Thank you very much. Very interesting. We are working with your paper. We are from TUM, and we like it very much. I showed it to a couple of students.
That's good.
I have some questions. So on the data set there, as you showed, some underrepresented aspects as well, right?
Yep.
And maybe if you can switch to the slide at the very beginning, it helps maybe for the context. So you have listed the amount